Right, the problem that we're looking at now is what happens when we have to find out if a reaction is redox. Now in the previous example that we looked at, we put it into an ionic form, and then from there the information was given to us. Now what happens when the information is not given to us? So what happens is we have something what we call an oxidation number. Right? It's an imaginary type of number which we assign, which could give us the information that we need to see how this whole sort of system works. Right? So what we're looking at is when we talk about the oxidation number, it's linked to valency, which is also linked to the charge on ions. Right. So it's an indication. So when I look at the oxidation number, it's an indication of the richness of electrons. Right? And this number signifies a charge or the number of charges. So it's rather the number of charges an atom would have in a molecule if electrons were transferred completely. Now when we look at things that are covalently bonded like hydrochloric acid and they're sharing electrons, we can assign oxidation numbers where we pretend that it was ionic and what would the hydrogen and chlorine look like. Right? So these oxidation numbers you have, or the rules, right? The rules, you have to know them, because if you don't know it off by heart, when you get a reaction in an exam, you're going to have a lot of issues because you won't know what to do from that point onwards. So what chemists have done is they've devised this, it's a useful, what we call it, it's an accountancy. Right? It's an accountancy tool to help us keep track of electrons and compounds in reactions. So it's there to keep track of electrons in compounds and in reactions. Right? This is particularly important in redox reactions because we know that two things are happening. We have atoms which lose electrons and we say they're becoming oxidized. Oh God. Oxidized. And we have compounds that gain electrons and that becomes reduced. Right? Each atom in a molecule is assigned an oxidation number. Sometimes we call them it can also be called the oxidation state. Right? It's a set of rules. So that's like solubility rules, very similar in you have to know the rules. Right? So this is either a positive charge or a negative charge. So let's do it like this. Let's write this down. This is the positive or negative charge the atom would have if the molecule was ionic. Right? Important. So let's have a look at the different types of rules. I'm going to go through these oxidation rules with you, but please, I'm going to add to it, so don't write everything out and then you realize we're adding on. So I'm going to address each one. So the first one says, it says the rules should be used in this order. This is important. The higher the rule, the higher its priority. This is very important. Because we have exceptions to the rule, we have to make sure that we follow what comes first. So there's 9 rules. There's more rules than this. I'm going to go through all of them with you. Just bear in mind that we have the situation. And let's look at the first one. The first one says an atom in its elemental form, example Fe or Cl2, graphite, etc., has an oxidation number equal to 0. So if I had, for example, for number 1, if I had Mg, or I had Na, or I had Ni, or even Cu, right? When it's on its own, right, it cannot have an oxidation number. So the oxidation number is going to be 0, and that's what it's saying over there. But this also works for diatomic elements, right? When I think of diatomic elements, they're two of the same things added to each other. Their charges are going to cancel out, right? So diatomic elements, we'll get to that one, right? Number 2, it says the sum of the oxidation numbers of all atoms in a molecule equals to 0, right? So let's have a look here. So if I look at any compounds, right? If I have, let's say, H2O, okay, let's use H2O. Let's use HCl. If I have a compound like this, right, and I add the oxidation number of H2 to the oxidation number of chlorine, it must equal to 0, right? So look here, I'm using the word sum. So if I have anything, HCl, I can have carbon tetrachloride, I could have, I don't know, water, and so on. So that's for rule number 2. Rule number 3. It says here the sum of the oxidation number of all the atoms in an ion equals the charge of that ion. So when I'm looking at ions, or I'm looking at polyatomic ions, right, they will keep their charges. So for example, if I look at SO4, oops, if I look at SO4 2 minus, right, if I add the oxidation number of sulfur, right, and I add it to the oxidation number of oxygen, right, then I must get a charge of 2 minus for SO4 2 minus. And it will all make sense when we get there, but we need to understand that idea. Right, number 4. Number 4 says the oxidation number of fluorine is -1, except in F2 where it's 0. So you focus on rule number 1. So can you see rule number 1 takes priority over rule number 4? Right, so for example, if I had a hydrogen fluoride, for example, versus having F2, then the oxidation number here is equal to 0. However, the oxidation number here and the oxidation number here differs. So here it's going to be always -1. And I know for all compounds it must equal to 0. So this one will definitely have to be +1. giving my molecule an oxidation number equal to 0. I'm just going to put a line through it because they're not O, 0. Right, the next one. The oxidation number of group 1 elements is +1. So if I'm looking here at anything in group 1, I'm looking at hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Right. They all have an oxidation number equal to +1. Right. The next one, number 6, the oxidation number of group 2 elements is +2. Please don't confuse this with charges, right? Anything in group 2, group 1 and group 2. Right, when I'm looking at group 2, please don't confuse this with charges. I've got your beryllium, I've got magnesium, I've got calcium, etc. All have an oxidation number equal to +2. Do not confuse it with charges. Right, these are oxidation numbers. Right, it says the oxidation number of oxygen is -2, except in the peroxides where it's -1. So if I think about it like this, there's no exception to this type of thing. So if I had, for example, H2O, right? In H2O, this is always going to be -2. But I know for compounds, I need an oxidation number equal to 0. So if this oxygen here is going to be -2, that means H2 has to be +2. So how I'm going to look at it is here. If I look at hydrogen, each hydrogen, so it's H plus H plus O. Each hydrogen is +1, +1, plus oxygen, which is -2. So if I had to add all of this together, right, I'm going to end up with 0, which is the oxidation number for all of the different compounds. So if I think of peroxide, if I have H2O2, right? Now here H2, right? I've got an H plus an H. And O2, I've got an O plus an O. Now we said that the rule says that all oxygens have to be -2. But the first rule says to me that all compounds must have an oxidation number equal to 0. So it's not going to work for us to have this oxygen as -2. So when we're dealing with peroxides, the oxygen's oxidation number is actually -1. So technically, if this is -1 plus another -1, I've actually got now -2, which means my hydrogens, when they add together, must give me +2. So if I'm looking at hydrogen peroxide, I can say H plus O plus O, right? And I've got +1 plus +1 plus -1 plus -1, because that's an exception. And I'm going to still get an oxidation number equal to 0. So therefore, the oxidation number of H2O2 is equal to 0. Does that make sense? All right, let's have a look at number 8. Number 8 says, the oxidation number of all halogens is -1. Right. Your halogens, fluorine, bromine, iodine, all have oxidation numbers equal to -1. Right. Please also remember that all of these are diatomic. So when they're in their diatomic state, which is F2Cl2Br2I2, then the oxidation number is equal to 0. So this situation here only applies, here if it is alone, right, or part of another compound. Not if it's alone, if it is a part of another compound. That's the only time it's going to be -1. Right, the next one. But remember with that one, because if I look at rule 4 with with fluorine, we must just make sure that we just double check that one. Right, the next one we're looking at is, right, the last thing we're looking at here is the oxidation number of hydrogen. Right, hydrogen is +1 when bonded to non-metals, and -1 when it's bonded to a metal. So please make sure that when you do something like this, you're very careful about how you bonding your hydrogen when it comes to metals and non-metals and so on. So let's just have a look at that one. So if I look at number 9, when we look at something like that, you need to understand that hydrogen is a non-metal. Right? So it's a non-metal that has a charge of H plus, right? One plus. But all metals are cations. So I'm never going to get a situation like that where I've got cations mean they all have a positive charge. In order to make a bond, it needs to be a non-metal and a metal. So great, hydrogen's a non-metal, but it has a charge of 1 plus, not 1 minus. So it's not something you're going to come across very often, having hydrogens bond with metals. But at this point in science, they found a way to compress hydrogen to a point where it becomes a metal. But it's not something we concern ourselves in this section. We do look at a situation, and I can give you another addition to the rule. We can say that hydrogen's usually +1, except in something called hydrides, where they become electropositive elements, particularly with metal cations, and then there'll be -1. So there is a situation where that can happen, and that is an addition there to your rule number 9. Right, so if I'm looking at that idea, please make sure that we understand what we mean by each of these different types of reactions. Even here when I'm looking at my rule number 8, which is looking at, I think, halogens, we must also understand about the halogens is that the halogens are always going to be -1, except when the central atom or when combined with more electron negative elements. Like, for example, I'm just adding onto your rules. Like I said, don't go and write everything out when there's little bits that need to be added in. Right, so you can put this here. Sorry, let me just move this down. Oops. And I can have this. I'm just going to put it over here. You can get that down. Oops. I'll put it here. We know that that's diatomic. There we go. Right, that's important. I'm just adding on to these rules before you go and write out everything. Other rules that we can look at is okay, no, that's fine. So this is all that we're looking at, and now we're going to have a look at the next section where we actually get to work with how do we assign these oxidation numbers, how do they work, what happens if I have an element, how do I decide which number goes where, depending on these rules. All right, let's have a look here. You've got your 9 rules. I've given you a little bit of a summary here. You can take it down if you want. It is useful to have a lot of information because at some point you're going to have to memorize all of these. Right? This is a shortened version or summarized version, but you still have to know the different rules. Let's look at the first one. The first one I've got here is aluminium fluoride. Right? With aluminium fluoride, I need to make a decision. I want to show that the oxidation number. So I know that the oxidation number of any compound must be equal to 0. Right? So let's have a look here. How do I get there? How do I get it to be 0? So if I assign oxidation numbers, if I look here at the compound, it's aluminium fluoride. I know from rule number 4. So I'm looking at rule 4. Rule 4 says if I have fluorine, it must be in -1. So over here, my charge of fluorine is -1. But I have 3 of it. So -1 times 3 gives me -3. Right, so I've got that. The second thing that's happening to this fluorine over here, it's attached to the aluminium. Now I want the oxidation number to be 0. So for aluminium, the aluminium's oxidation number has to be +3. So that the overall charge is +3, right, plus 3 times -1, which is going to give me an oxidation number. The oxidation number is equal to 0, right? So when we work with these, you have to take into consideration subscripts. You have to take into consideration which rules we're looking at. Right, let's look at the next one. The next one is ammonia. Right, ammonia is NH3. So I have a hydrogen attached, you should be taking all of these notes down, to a non-metal. Right, it's attached to a non-metal. If it's attached to a non-metal, then H has a charge of 1 plus 1, right? So if I look here, it's +1, but there's 3 of them, so times 3 gives me +3. So what does that tell me now about my nitrogen? If I remember the rule 1 says that the sum of all oxidation numbers of atoms or ions in a neutral compound must be 0, which means that this nitrogen has to be -3. So what I'm going to end up with here is that to get an overall charge of 0, I've got -3 plus 3 times 1, which is going to give me 0. So my oxidation number is then equal to 0 for ammonia. Right, if I look at NH4 plus, right, this is a bit different. I want my overall charge to be equal to +1. Yes, because if I look at my rules, and I'm looking at rule 3, it says the sum of the oxidation numbers of the atoms in an ion, and we're talking about polyatomic ions, must be the charge of that ion. So if I go here, I want the overall charge to be 1. Now I have got hydrogen attached to a non-metal. So that's also a rule, which means all my hydrogens have to be +1. The ion has a charge of +1, right? So now when I'm looking at the situation, let's just have a look at what's happening here. I've got NH4 and I've got 4 hydrogens here, right? So I've got a charge here of +1 times 4, right? So I'm sitting at +4. Now I want my overall charge to be +1. So if I'm looking at the nitrogen has to be a number when added to +4 equals +1. So if I'm looking in terms of integers, that means that my nitrogen has to be negative 3. So negative 3, just pen this down. Right. I'm going to have negative 3, negative 3 plus 4 is going to give me plus 1. Therefore, the oxidation number is equal to positive 1. Here's my answer there. There's that answer there. So it makes sense. Alright, let's have a look at the next ones. Alright, if I'm looking at the next one, which is chlorine, what I'll notice about chlorine is that it follows rule 1. What I have here is elemental chlorine. And I know about all elemental chlorines, according to rule 1, is that the oxidation number is equal to 0. Right, that's that. Let's have a look at the next one. ClF3. Right, I've got chlorine and fluorine here. Right, so the first, because rule 1 comes first, the fluorine has to take precedence. So I know that fluorine is negative 1 and there's 3 of them, so times 3. So I'm left with negative 3. I also have another rule, so I know that fluorine has an own oxidation number of negative 1 and rule 1 comes first. Oops. Rule 1. Right, I also know that chlorine is a halogen. And all halogens are equal to negative 1. Now remember what we said. What rule is this? This one. Oops. The rule here is rule number 8. So this comes from rule 8. Now remember what we said. These two rules are now contradicting each other. Because technically, if I've got negative 3 here, this has to be negative 1. But rule 1 or rule 2 says, so if I look at the sum of all elements in a compound must equal to 0. Right? So let's see what I've got here. That's going to give me rule 2. Right. So can you have a look here? That first we have, this is rule 4. Right. I've got rule 2, which means I have to make sure that this whole thing equals to 0. Right. I've got rule 4, the fluorine has to be negative 1, which means that this rule here, that's the rule that comes last. We're not really concerned with it. We have to make sure we're following rule 2 and rule 4. Right? Because 4 has a higher priority than 8, 2 has a higher priority than 4. So, for the chlorine, now we can't say that the chlorine is negative 1. We have to make sure that this thing equals 0. So the chlorine in this instance, instead of being number 1, negative 1, it's actually going to be positive 3. So now I have a situation where it's 3, positive 3 plus negative 3, which is going to equal to 0, and therefore the oxidation number is equal to 0 for that compound. And let's have a look at the next thing. Right, if I'm looking at this one, got a little bit of, what do I have here? Yes, a little bit of a charge. So I know that fluorine has an oxidation number of negative 1. I know that the iron must have a charge of plus 1. And I know that chlorine is the thing that has to operate around this whole situation. So what I'm going to be left with now is a setup that looks like this. Whoa. Where fluorine is negative 1, which is great. Negative 1. There's 4 of them. So technically it's sitting at negative 4. I want my overall charge to be equal to positive 1. So the only way to even that out is my chlorine. My chlorine has to be positive 5. So I end up at positive 5. Oops. I end up at positive 5 plus 4 times negative 1. And it gives me an oxidation number that is equal to positive 1. And let's have a look at the next one. The next one I have here, just move all of this out of the way, is the same setup, except this time the overall charge is equal to negative 1. Same thing. Fluorine, the rule for fluorine takes precedent. So for the fluorine, I must have the oxidation number equal to negative 1. The ion charge for this one is going to be negative 1. Right? So now I'm left with a situation where I've got this negative 1. It's negative 1 times 4, bringing it to negative 4. And we want the overall charge to remain negative. So our chlorine must have a positive 3. So positive 3 plus 4 times negative 1 is going to give me negative 1. So therefore the oxidation number is now equal to negative 1, which we wanted it to be this whole time. So can you have a look here in these 3 examples? In the first one, chlorine is positive 3, right? In the second one, chlorine had to be positive 5. In the last one, it had to be positive 3. But each of these situations were all 3 very different. So you need to make sure that you know how to use these rules, know how the rules work, and how we're going to sort that out. And let's look at the next one, nitric acid. So if I have nitric acid, I've got H here, which is a non-metal, and I've got, let's look at my rules. So I've got H, oh gosh, it's in yellow. I've got H, I've got N, and I've got O. Right. If I check my rules about H, my rules about H is rule 9. Right? And rule 9 tells me that because the H is bonded to a non-metal, it must be a charge of 1 plus. Great. Nitrogen, I know nothing about. Oxygen tells me, if I look at rule 7, right? If I look at rule 7 is telling me, let's just go here. Rule 7 says that the oxidation number of oxygen is negative 2, except in peroxides when it's negative 1. Now it's nitric acid. It's not a peroxide, right? So I'm just going to reduce this a little bit. Right, so if I look at rule 7, I know that the oxidation number here of oxygen must be equal to negative 2. Right? So now I've got to sort this out. In the end, I've got a compound, which means overall it must be equal to 0. So let's have a look here. So for oxygen, you have negative 2 and you have 3 of them. So technically over here you have negative 6. Right. The next rule, so there's rule 7. You work with that one. The next one says rule 9. So rule 9 tells me that my hydrogen over here has to be plus 1. Great. And my overall has to be 0. So in order to get an overall of 0, when I add all of these numbers up together, I must equal to 0. So if I'm looking at my nitrogen and I've got negative 6 plus 1, I'm missing a plus 5. So in my whole situation now, in order for this nitric acid to become neutral, I need to say positive 1 plus 5 plus 3 times negative 2, which is going to give me an oxidation number of 0. All right, let's look at the next one. We've got N2O4. just going to pan these out of the way so that it's not a bother for me. Right. If I'm looking at N2O4, again, I need to follow the rules. I know that according to rule 7, in terms of the oxygen, so I've got oxygen and I've got nitrogen. Because of rule 7, it tells me that my oxidation number is -2 for oxygen, right? Unless it's a peroxide. So if I'm following that situation, I've got -2 here. Oops. I've got -2 and I've got 4 of it. So -2 times 4 is -8. But I've also got myself here a compound. So the overall charge has to be equal to 0. So when I'm looking at that situation in terms of my nitrogen, and if I look at my nitrogen, how many nitrogens do I have? I have 2. So of these 2, they must have a charge. Each nitrogen must have a charge, if this is -8, must have a charge of +4 and +4. So overall, the N2 must be equal to +8 in order to cancel out. And in an exam situation, they can ask you, what would be the charge of each individual nitrogen? Right? And then you'd have to say nitrogen has to have an oxidation number of +4. So it's going to be 2 times +4 plus 2 times -2, which will give you an oxidation number of 0. All right, let's see this next one here. The next one is NH2 plus OH. Right, this is a little bit of a different one. Again, let's have a look at the different things that we're dealing with. I've got oxygens, I've got hydrogens, I've got nitrogens, and of these I know some rules. I have a rule for hydrogen, which is rule 9, that it's +1 if it's added to any non-metals. Nitrogen's a non-metal, hydrogen's a non-metal, oxygen's a non-metal. Great. I've got rule for the oxygen, I've got rule 7. So rule 7 trumps. So here in this situation, my oxygen must have a charge of -2. And because I have a compound, I know that according to rule 2, I must have an oxidation number overall is equal to 0. Right, and then the nitrogen, we don't know. So if I'm looking at this situation, my O has a charge of -2. My hydrogens have a charge of 1 each. And there's 2 here. So let's have a look here if I'm going to write it out. But NH2OH. So here, for the oxygen, I've got -2. Great. Here I've got +1. Here I've got +1 times 2. So overall, I've got +2, -2, +1. So I've got +3, -2. So I need this situation to equal out and be 0. And the only way to do that is that the nitrogen must be -1. So how that's going to look, oops, just get this out of the way and move this in here. I'm going to have -1 that's going to come from my nitrogen because it has to even out, because technically I've got +3 and -2, so I need another -1. Alright, so I've got -1 from the nitrogen plus 2 times +1, which is your H2, plus -2, which is your O, plus +1, which is your H. And I'm left with this sort of setup. Right, N2O. N2O is oxygen, we know, must be -2. And you've got 2 nitrogens. So if your nitrogens, so if you have -2, each of your nitrogens has to be +1. And if each of your nitrogens are going to be +1, you're basically going to have 2 times +1 plus -2, which should give you an overall oxidation number of 0. But if I'm looking at NO3 minus, I know NO3 minus that my overall must be equal to -1. Over here I've got oxygen bonded to nitrogen, and I know that this value should be -2, and I've got 3 of them. So I end up at -6. Now nitrogen needs to be something, whatever it has to be, has to give me a situation where I end up with a -1. So the number has to be a positive number, and it has to cancel out in exactly the right way so that I can get a situation where I have -1. So the only way to do that is to make the nitrogen +5. And I'm going to end up with a situation that looks like this. +5 plus 3 times -2 is equal to -1. Right? So when we're doing these things or these situations, you need to make sure that you understand how this works. For example, even if I had NO, nitrogen monoxide, I know that this is going to be -2. And because this is a compound, it has to be neutral. So this one has to be +2. So -2, or rather +2 plus -2 is going to give me 0. So the oxidation number here is 0. So you need to work with the rules, because if you don't work with the rules, you're going to be stuck in a situation when you are not sure what is going on. Alright, if you make your way to the next video, we are going to look at redox reactions, how we work with these redox reactions, how we can be influenced to do redox reactions in terms of, if I have an equation in front of me, how do I decide, is the reaction redox or is it not redox, using these oxidation numbers. So we're going to get quite actively involved. So please make sure you have these rules, you've done these examples, you have some point of reference before you go to the next video.